Welcome to lesson 4.4, Composing Reflections over Parallel Lines. So we've already looked at how to reflect points and figures over a single line. Now we're going to look at compositions of reflections over more than one line, and these lines in this lesson are parallel to each other. So the first activity where it says reflect over parallel lines, numbers 1 through 6 here, what I'd advise for you to do is pause this video, take out a sheet of blank paper, and actually go through these 6 steps to help you visualize the rest of this lesson. So obviously with this being a video lesson, I digitally can't fold the paper for you. So I'm trusting that you'll pause the video, try these 6 steps on a sheet of paper. Then we'll move down, assuming that you did the activity, into the next part, the language composition. And the reason that this activity is important is the language composition is based off of that. You can also look in the book lesson to help you with some visuals for this. But in activity 1, it says triangle ABC was first reflected over line M to form triangle A prime, B prime, C prime. Triangle ABC prime was then reflected over line N to form triangle A double prime, B double prime, C double prime. This can be expressed using function notation by writing the following. So if we wanted to start off with that first part of ABC reflected over line M to form the image triangle A prime, B prime, C prime, it's written this way. Triangle ABC, whatever's in parentheses, is being reflected over line M, and our result is triangle A prime, B prime, C prime. Then the second step in that reflection notation would be A prime, B prime, C prime being reflected over line N to give us triangle A double prime, B double prime, C double prime. Now, if we're doing a series of reflections, we can combine these notations into a simpler form. So one way we can do that is these two equations can be written as one equation by substituting ABC reflected over M for the triangle A prime, B prime, C prime in the second equation. This one equation fully describes the relationship. So we would still keep the reflecting over N on the exterior, but we're replacing this part in parentheses with the left-hand side of the first equation. So what this would become is the R subscript N, and then in parentheses, R subscript M, more parentheses, triangle ABC, end parenthesis, and our final result being A double prime, B double prime, C double prime. So the way that this notation would read is triangle ABC reflected over line M, then that reflected over line N results in triangle A prime or A double prime, B double prime, C double prime. So this is our notation for the two reflections. The first one's on the interior, second one's on the exterior. So we could use that same notation to see the relationship between the individual points or parts of the triangle. So for example, point A reflected over line M, then reflected over line N, gives us point A double prime. So now we are going to get into this idea of composites. So as it says, the composite of a transformation S and a second transformation T is denoted by this T open circle S. And this notation right here, the T open circle S, the composite notation, is the same thing that maps point P to end up this way. So this then is P resulting in S resulting in T. So what this is actually read as, the T composite S, is read T following S. So T follows S. So whatever's on the right happens first, the left would be second. So then this one would be read as T of S of P. So this little small circle in the middle, the operation denoted by that little circle is called the composition. Any transformations can be composed, but for now we're only dealing with reflections. So we're going to look at how composite notation goes with our standard language of reflection notation up here. So how do we go from something like this to composite notation? So let's look. So if we are reflecting point A over line M and then over N, resulting in A double prime, that's the same exact thing as using composite notation. So instead of the parentheses, we're going to use the composite or the composition little circle right here. So we would then have, the way this would read is point A reflected over M and then reflected over N results in A double prime. Or like here, how it says the T composition S is read as T following S. So this would be the reflection over line N following the reflection over line M of point A gave us A double prime. So the first transformation or reflection is written on the right-hand side of the composition. Whatever is in parentheses is what we're reflecting. And then we have a translation. So a translation is the composite of two reflections over parallel lines. In other words, it's a slide or a shift either vertically or horizontally. So simply put in geometry, you can think of a translation. It's that result after we do composites over parallel lines, but really it's just a slide or a shift of the original figure. Just like you would see in that original activity from triangle ABC to A double prime, B double prime, C double prime, it was just a slide down the paper or a shift. So we get to a couple pieces of the translation then. The distance or magnitude. That's found by measuring the distance from any pre-image point to its image point. So if we would measure the distance from, using that first activity, point A to point A double prime, that would give us the distance or magnitude. Then the direction would be given by the ray from any pre-image point through its image point. So drawing a ray from a pre-image point through the image point gives us the direction of the translation. So we're going to try to make sense of that looking here at example 1. So in example 1, it says find the distance and direction of the translation that mapped triangle ABC onto triangle A double prime, B double prime, C double prime. So if this is our drawing over here, we want to find the distance and direction from triangle ABC here that resulted in A double prime, B double prime, C double prime. So how can we do that? The first thing you want to do is draw a ray from one point on the original to its corresponding point on the final image. So they went from A through A double prime, and a ray has an endpoint going forever in one direction. So you start on the original, draw the ray to the final image. And then we put the arrow on the end. So simply this ray here tells us the direction. The magnitude is the distance then from A to A double prime, or the length of the segment A to A double prime. So if we had a way to measure this, you would just lay a ruler or a measuring device from point A down to A double prime to give the magnitude. In this case, I don't have the measurements, so the magnitude simply is A to A double prime. So then if we look at the ray, that tells us the direction. The distance between the points tells us the magnitude. Then we have our two-reflection theorem for translations. So what the two-reflection theorem for translations states is if M is parallel to N, the translation, reflection over N following reflection over M, so first reflecting over M, then N, has a magnitude that is 2 times the distance between M and N in the direction from M perpendicular to N. So that sounds confusing, but we're going to look at it in example 2 and 3 to make sense of it. So let's go down to example 2 and start to make sense of all these different pieces of info. So example 2 says, let P be the line described by the equation y equals 3. So the line here, y equals 3, is line P. And Q be the line described by the equation y equals 8. So right up here would be line Q at y equals 8. Then it says, describe the translation, reflection over P, composite reflection Q. So reflection over P following the reflection over Q, and compare it to the translation, flipping that order, RQ following RP, so reflection over Q following reflection over P. So the first thing we want to think about is that distance from the line P to Q. And the distance here, 8 minus 3, tells me these are 5 units apart. So my distance from P to Q is 5 units. So the magnitude of any reflection over Q, then over P, or vice versa, over P, then over Q, they're going to be twice that distance. So whatever the distance is, our magnitude's double that. So our magnitude would be 10 units. Then the direction of RQ following RP. So if we were going to reflect over P, then over Q. So if I had a point right here, reflecting over P, then over Q, my direction would be vertically up. So in this case, we would just call that up. Then the direction of the composite RP following RQ, so first over Q, then over P, would be down, because we'd go over Q, then over P. So the comparison of these two different translations is they always have the same magnitude, they just have opposite directions. And then in 3, so we're using the diagram here. It says, prove that it's true that the distance between the pre-image A and its translation image A double prime is twice the distance between the two lines. And we were given the idea that N and M are parallel to each other. So if N and M here are parallel to each other, we're going to come up with an idea that proves the distance from A here to A double prime is twice the distance from M to N. So the distance between lines M and N are simply A plus B. We have an A and a B here, so A plus B gives us the distance between M and N. The distance between A prime and line M was the letter A, given to us right there. The distance from A double prime to N was 2A, and it didn't print very well, but that's a plus B. So that's 2A plus B here, and A there. And then we have the other piece of info, the distance from A to A double prime we can also look at. So from A here to A double prime, I have this B plus the 2A plus B. So that would be B plus B, or 2B plus the 2A. So the distance from point A to A double prime is 2A plus 2B. Well, what we're trying to prove is the distance from A to A double prime, right here, is twice the distance between those lines originally. So if A plus B is the distance between M and N, then A to A double prime, 2A plus 2B, proves that that is twice the distance of this. So whatever the distance is between the two parallel lines, your magnitude is always double that. So what they did first was reflected A over M, and then reflected A prime over N to get their final image.